Okay, so RC circuits, if you guys remember, it is a circuit that has capacitors and resistors in them. There's like this time delay where charging them and discharging them takes some time. And you can calculate that time delay with this RC constant, which is just RC. I didn't write that here, but I guess I can write that. The time con the time constant is R multiplied by C, or if you want, all the resistors that are involved in charging multiplied by all the capacitors that are involved in charging. So that won't always be all the resistors, and that won't always be all the capacitors. So you need to decide which capacitors, which resistors goes in the calculation. Um, Essentially, it's just slow charging, which is different from when it's just capacitors in a circuit, where the capacitors charge instantaneously or practically instantaneously. What we need to remember is that the voltage across the capacitor is going to be equivalent to the voltage across the branch that it's in. Okay. I have an example, but it turns out that it's impossible because I gave it to the other class and we scratched our head. That class, by the way, it's group 3. They must think I'm like dumb or something because every time they're always the first group I teach anything to. So I always all the mistakes show up there, and then I have to fix them, and you guys get like the more refined version. I feel bad because that's how it was all semester, but anyways, they might not think very highly. Anyway, so yeah, this problem is not possible, but we will try to describe it a little bit. Okay. Um, First of all, I want you guys to take a look at the circuit, and it's different from every other RC circuit that you guys have done because it's got multiple capacitors in it. Um, I want you guys to tell me qualitatively, because mathematically you don't have the tools to be able to solve this one. You need something called advanced calculus, which is taught in your second year university, to be able to solve it. It's called differential equations, and okay, so we just don't have it. But you can tell me qualitatively what's happening here. So take a few moments and look at this circuit and tell me how it's going to charge, and do the trick that we did. You know, when we said that when a circuit just starts charging, the capacitor behaves like a yeah blank, and then keep use that logic to solve this. All right, and see where you get. Once you've rationalized an answer for what's happening when it's charging, try to figure out what's happening when it's discharging. And for it to discharge, you have to assume that there's a switch here to open. So when I open that switch, it starts discharging. Okay, so tell me if you can quantify, or sorry, not quantify, but qualify what's happening. Wait, huh? That's an interesting idea. So Noemi says that C1 behaves like a short circuit, which is right. So if C1 is acting like a short circuit, there won't be any current going into C2. So therefore, C2 will not charge. And therefore, when you're discharging it, C1 will discharge it into C2. Yes and no. There's a lot of good things there. What I like that you said is that C1 behaves like a short circuit. And so therefore, C2 won't charge right away. But again, now someone else add more to it. What happens when, let's say they charge at different rates. Let's say C1 had to charge first. What's going to happen after C1 charges? Then C2 will charge, all right? So C2 will charge at a different rate. However, does C1 need to be fully charged in order for C2 to start charging? Because as soon as C1 is slightly charged, the voltage across it is no longer zero, and therefore there has to be a redistribution. So that means that there's just a time delay between C1 and C2, right? And C2 is just going to charge a little bit later. What happens when they're both fully charged and I open the switch? What do you think? The exchanger, well, let's look at these parallel plates. Which one on C1, which one's going to be positively charged? The top one or the bottom one? The bottom is going to be positively charged? I think it's the other way, because your positive charges move this way, and so the positive charges are going to collect along here. They're going to collect along here, and therefore this is going to be negative. What's going to be the voltage across each one? Are they in parallel? So are the voltages going to be the same? All right, so let's just say this is going to be VC1, and this is going to be VC2, and that VC1 is equal to VC2. So how is it going to discharge? It just won't, all right? Because the charges need to go to an area of lower potential, and if this loop is the only loop that's available for the current to go, and both capacitors are charged to the same voltage, then there's going to be no electromotive force to move charges from one place to another. So all the charges are going to remain stationary, and that's it. So yeah, I only realized that while I was showing the other group, so I was embarrassed. Questions on this? Being able to qualitatively describe that is something that you should be able to do. Mathematically, though, this was not at your level. Questions? All right, so after RC circuits, that was the end of circuits, formally speaking, because we do go back to circuits with inductors and all that stuff. But this is when we started talking about magnetism, and there's a few key concepts about magnetism that's really important. One is that there are two different kinds of magnets, regular bar magnets and electromagnets. What's the difference between a bar magnet and an electromagnet? Who can tell me? Yeah, exactly. Exactly. So a bar magnet is permanent, while an electromagnet can be turned on or off depending on the current, and the strength of it can be manipulated and everything. Someone in the other class asked me, what makes a bar magnet or a permanent magnet magnetic? And I had a hard time answering that, so I did some research. And do you guys remember when you guys did chemistry NYA, there was a concept of quantum numbers, and one of the quantum numbers was magnetic spin, m sub L. So that, in fact, it comes down to that the spin of the electrons produces a magnetic field that is either always there because of the material or not. Magnetic field lines. Oh yeah, so magnetic field lines. First of all, magnets produce magnetic field lines, whether they're bar magnets or electromagnets. They're always drawn from north to south. So how is it drawn for electric field lines again? How are electric field lines drawn? If I had to draw a direction to it. High to low potential. Yeah, that's correct. Or just positive charge to negative charge. And so magnetic field lines have a similar kind of thing. They go from north to south. So we have to remember that a charge that's not moving is not producing a magnetic field. Okay, the charge has to move. So if I were to ask you, does a Van der Graaf generator produce a magnetic field? or like the big ball part of the Van de Graaff generator? Yes or no? Yes? Why? Where is the movement of charge? Okay? And yeah, okay, in the belt there's going to be some movement. I'm talking about the ball itself once it's charged. Is it going to have a magnetic? No, that's not going to have a magnetic field. But you're right. While it's charging, I suppose you can say that there's a movement of charge, and therefore there is a magnetic. But once it's charged, it's no longer. By the way, a Van de Graaff generator is what we call a spherical capacitor, right? Because it holds a charge, and the charges aren't going to be equal on both plates because there's an inner plate and an outer plate, and so therefore there is a net charge on the outside. The magnetic force is measured when a ferromagnetic, sorry, you get magnetic force, right, when you put something that can be magnetized in a magnetic field, and then it feels a force. Obviously, this is one of those things that you know from when you're kids. Similar poles repel, and opposite poles attract. So the North Pole attracts the South Pole attracts the North Pole, and the North Pole and the South Pole attract or repel each other, rather. Any questions on that? This was a very theoretical lesson that we did, so I don't have any questions on it. It's going to be kind of like memorization. But then we talked about magnetic force and what it means to have a moving charge inside a magnetic field, and a moving charge inside a magnetic field will produce, will feel a magnetic force. And if that charge is free to do whatever it wants, meaning it is not constricted to a wire, then that charge is going to feel a centripetal force. All right, so it's going to be a center-seeking force, and the electron is going to be, or not the electron, but the electron or the proton or whatever the charged object is going to feel circular motion. Yeah, that's when you have a moving charge, right? That's free to move wherever it wants in a magnetic field. All right. So what I mean by free to move wherever it wants, I mean it's not in a wire. So in a wire, it's constricted to going only down the wire or backwards in the other direction. But if you have a free moving charge like in space, it's able to go in 3 dimensions, and you put a magnetic field there, then the charge is going to go into a circular motion. Okay? And you can determine the direction of the force and the direction of the motion with your right-hand rule. It's a cross-product relationship, so you need to be able to do this kind of manipulation. And someone asked me, do you need to be able to do a cross product of a matrix? The answer is no. I won't give this to you in IJK notation. But you will need to know this in regular, like, what's it called when it's not IJK notation? Like vector notation. I don't know. Actually, I don't know. So we'll do an example of it, and then you guys tell me what the name of that system is. Then I'll be wiser. Any questions on this? So let's do an example. An electron is moving at 21,000. So by the way, this is 21,556. I know in French, you use the comma as a decimal point, but not in English. Okay, in English, a decimal point is a dot, right? So this is just separating the thousands. So this is moving at 21,556 meters per second in the north 23 degrees east direction, in a magnetic field pointing north 1.1 degrees west. That has a magnitude 49.5 microtesla. And I'm asking you to determine the direction and the direction and the magnitude of the electron. Okay. When I say electron, is that left hand or right hand? Left hand. Okay, good. So now, what do you call this vector notation? When I write a vector like this with degrees and stuff like that? I don't know. All right, so let's draw this situation and see what happens. So I have my velocity going in the north 23 degrees east, so that's like this way. So this is north, east, west, south, and this is 21,556 meters per second. And I have my magnetic field, which is somewhere in that direction. This is 1.1 degrees. And this is going to be 49.5 degrees. Okay, perfect. So now I need to figure out two things. I need to figure out its direction, and I need to figure out its orientation. Who can tell me its direction? Remember cross product rules. When you have two vectors that you cross multiply, the resultant vector is going to be what? What characterizes the resulting vector? Is what? It's going to be a normal to both of those vectors. So it's going to be at 90 degrees to both of these. Which vector, there are two possible ones, of which we're going to choose one of them. Which direction can you have as a vector that's 90 degrees to both of those vectors? You know what I mean? That's one of them. The other option is out of the page, yeah, into the board or out of the board. Now we have to figure that out, which one of those two it is, and let's see if we can do it. Let's thumb in the direction of the velocity, and our fingers in the direction of the magnetic field, and so therefore the force is going to be in which direction? Into the board. All right, great. So magnetic field B is into the board. Oh yeah, sorry, force FB. Yeah. Okay, great. If this force is into the page, we have to characterize that because that's not a real direction, right? Into the page is not a real direction, especially if I'm talking about northeast, southwest. So what's into the page if I'm talking about northeast, southwest? That, it's downwards, okay? So you have to imagine, if we're looking at this as like a map of Canada, let's say, all right, and north is obviously up in the map and south is down in the map. If you look into the page, that's like going deep into the ocean or into the ground. So yeah, downward. So we know that the force that's being made here is going to be downward. And okay, so now we just have to find the magnitude. And that's going to be force, kinetic force is going to be equal to the charge multiplied by the velocity multiplied by the magnetic field plus the sine of the angle between them. All right? What's the charge of an electron? 1.6. What's the angle that separates my two vectors? 24 square, 24.1. What if you were to use sig figs? What's the rule that you need to use when you're adding numbers together? The what? Yeah, exactly. It's you take the one with the least number of decimal numbers. Which is the one with the least number of decimal numbers? 23. So that's what your answer is going to have. Your answer is going to have 0 decimal number. All right. It's not because it's 2 sig figs each that you're going to get an answer that has 2 sig figs. It's really because of the least number of decimal numbers. That's the addition and subtraction. Yeah. You could if you want, in which case here you would write 24.1 and in brackets here you can write 266. Name show. Okay. How many sig figs is 1.6 times 10 to the negative 19 have? Yeah, okay, it's a constant. The other two are not constant, so the first one's got 5, the second one's got 3, and your angle's got 2. So your answer is going to have how many? 2, yeah. Give me an answer now. Units, direction, down. South, south is actually that way, whereas down is that way. All good? Okay, moving on. We had a question, we had a topic where we just applied this magnetic force and this, now we combine it with electric force. And we use this concept in mass spectrometers. And in mass spectrometers, first of all, the objective of a mass spectrometer is to identify objects by their mass. And so it's going to take a different circular trajectory in the third region depending on its mass, but it's got to get there first, all right? So the mass selector is the last piece. The middle piece is called the velocity selector because you choose the particles based on their velocity, and you can manipulate this with the electric field and with the magnetic field. And the first region is the part that accelerates the particle. Okay. There's two things though. One is that it has to be a single atom, has to be a single atom, and two, the atom has to be charged. If you remember, the first region of a mass spectrometer, the particle is accelerated using parallel plates and a voltage drop, right? And that voltage drop, or sorry, maybe not a voltage drop, but a voltage difference, that voltage difference only applies accelerated force to something that's charged. So if it's neutrally charged, then it's not going to feel a force. Yeah. Nope. Because remember, something that feels a force in the magnetic field is a moving charge. So if it doesn't have a charge, its Q is zero. Any questions on this? No problem. So the mass spec is applying a 266 newtons per coulomb electric field and a 395 microtesla magnetic field to keep a doubly ionized particle in straight horizontal motion. Determine the voltage across the parallel plates in the first region. So first of all, what's a doubly ionized particle? Yeah, it's double of what though? That chargé? Yeah, okay, exactly. So it's got a double charge in the sense that it's got two charges. Whether it's two negative charges or two positive charges, in this case, it's not really mentioned, though it's not really a part of the question, so we don't need to worry about it. How do I figure out, well, first of all, what steps do I need to take in order to solve this problem? You can tell me that. First, find the velocity, and then what is the velocity going to give us? The acceleration? We don't need so much the acceleration here. We could use acceleration, but it would just be like 5 extra steps to get to something that we can do in one step. Yeah, you find out the kinetic energy. And where did you get that kinetic energy from? Potential energy, and the potential energy is coming from a voltage difference. Okay? So let's do that. How do you find the velocity using this equation? In fact, let's start earlier than that. What's happening in that velocity selector? Which two forces exist? Yeah, exactly. And if it's going to remain in straight trajectory, what does that mean about the magnetic force and the electric force? Equal and opposite, exactly. So let's write that. Electric force is going to be equal to magnetic force. Okay? And we know that the electric force is Q times electric field. And magnetic force is Q times, this one is, yeah, exactly, QVV. So I can cancel out my, oops, not my V, but my Q's. And so I'm left with E is equal to VB. And if I isolate V, I get V is equal to E over B. Yeah? Can you guys please do this? I should get a really big velocity, maybe in the millions. Or close to a million, maybe hundreds of thousands. Combien? 173? Okay. How many sig figs should this have? Yeah. Anyone travel or drive here from downtown or from downtown direction? How bad was it this morning? That was ridiculous. It took me 55 minutes, something that normally takes me 18. Crazy. It's going to be like this for a year and a half. You're graduating. Where are you going to school next year? Okay. Okay, so we got our velocity, and Gabrielle said that that's going to give us some kinetic energy. That's great. It's true. We have some kinetic energy. I realized that I didn't give you a parameter. I need to give you mass. So mass I'm going to give you is 9.1 times 10 to the minus 26. Okay. So that kinetic energy came from potential energy. How do you find electric potential energy again? What was the formula for that? Yeah, charge times delta V. And delta V is what we're solving for. So this is really convenient because that means that 1/2 mv squared over q was delta V. Put your hand up. I'm making up a mass because this is not necessarily an elemental charge. This could be an atom. I like that you're paying attention to that though. So let's find an answer for this. Can someone give me an answer for delta V? Should be a big-ish number. Combien? Ooh, that's big. 204 000. No, it's I just made up the numbers, so I have no idea. How many sig figs? Ah, you're right. So I forgot to do the multiplied by 2. Oh, does that change your answer, Gabriel? Il faut faire fois 2. Il faut faire la charge fois 2. La charge. Même chose? Okay. How many sig figs? 3? 2, exactly, because of the 9.1. So 64,000 units? Yep. Ah, you're right. I'm not paying attention. Units? Oh. Yeah, no, I mean. Ça, c'est la masse expérimentale of an atom that I chose. It's not any, it's not one proton or it's not one electron. Because if you remember, a proton is times 10 to the negative 27, not 26. So this is like many protons. Okay. Okay, so perfect. Our voltage difference is 64,000 volts. That's kind of unrealistic because we can't really generate that with regular wires. Okay, uh, we said that charges feel a force, and therefore current must also feel a force because current is just a movement of charges, and by definition, charges that are moving will feel a force. So we extrapolated this information, and we see that the relationship is this current multiplied by the length of the wire in the magnetic field at whatever angle that is, and then you get the force acting on the wire. And if you have two wires next to each other, well, one of them is going to, well, actually, we haven't gotten there yet. That's the next slide. So I'll stop there. We need to remember that there's a loop that you go, if there's a loop that exists in a magnetic field, then that loop is going to feel torque and it's going to make it spin. And we said that that's what a regular DC motor is. You need this device called a commutator if you want this loop to continue turning forever and ever. So let's do an example. So it says here, a simple DC motor with a commutator made with 200 turns and a current of 0.33 amps is placed inside a 4 millitesla magnetic field. Graph the torque as a function of time for the above setup. And I'm saying that there is a commutator, in which case that the force, the torque is going to be, what is it going to look like? Yeah, it's going to be a wave function. Now the shape of this doesn't matter yet. So this is going to be in red. What's going to be on the y-axis here, by the way? And on the x-axis? Time. All right. So what's going to happen? Is there going to be more torque or less torque with respect to time if I decrease the amount of turns in my loop, in my whatever my motor? What do you think? The same, maybe. Someone have a different answer? Okay, so Zach, why did you say less? Why did you say the same? Okay, and why did you say less? Okay, so let's solve this right now. Here's my loop, all right? And forget about the direction of the current, it produces a magnetic field in this direction. If I have a second loop, it's going to produce its own magnetic field in that direction. So if I have two loops, I have two vectors together, and so on and so forth. So the number of loops does in fact add to the magnetic field. And in this case, does it make more loops less magnetic field or more magnetic field? Less. Oh, right, so let's do this in a different color. What's my graph going to look like? It's going to look the same. It's going to be a wave function again, except I won't reach the high peaks like I was before. I'll have really low peaks. What happens if I have a really strong magnetic field? Really high peaks, exactly. It's going to be the same thing, but you're going to have a huge amount of torque. Now what's going to happen if I lower the current? Smaller, less torque again. So I'm just going to, just for the sake of argument, I'm going to make it smaller than the, it doesn't really mean that for a fact. Someone in the other class asked me a good question. What kind of things could you do to this to decrease the frequency of the loops? You guys have an answer for that? So like to shrink like to squeeze the function together and make it like more frequencies, more turns per second or less turns per second. Sergio, what do you think? No? Yeah? Smaller loops, so if I decrease the area, it would have the same effect as these. So it's a good answer. The truth is, your answer is correct, and all these answers are correct, and we were wrong in drawing all of these graphs. The only reason why I didn't draw them differently is because you guys haven't learned how angular frequency works, unless you tell me you did learn angular frequency. No? You learned it a little bit here in my class, but not in math class yet, or not in physics class. When we do waves, you'll learn about this thing called angular frequency, and basically, you know how force is equal to m times a. You're going to have tau is equal to m times alpha, and alpha is angular acceleration, and torque is related to angular acceleration. So like when you increase torque, you're actually spinning it faster as well. So in fact, all of these should be changing the width of it, but we just haven't learned that yet, so I'm not going to touch it, and we'll leave it for next semester. Okay. All right. So Ampere's law is that a current actually produces a magnetic field. So before it was a current in a magnetic field feels a force. Now a current produces a magnetic field. And if I have some wire that's, let's say, coming out of the board that way, which direction is the magnetic field being produced? What what is that? Counterclockwise, all right? So you use your right hand, the thumb is sticking outwards, you follow your fingers to see where the loops are going. If I were to ask you, on top of this wire, at this point here, what direction is the magnetic field going? Yeah, directly left, okay? And over here, down, and over here, to the right, oops, to the right, and over here, upward. And last thing, if I were to go further away from it, would my electric field, or sorry, my magnetic field, will it increase or decrease? Decrease, exactly. Did you say English? No, okay, decrease. Yeah, decrease. Um, you decrease because you're further away from the source, obviously. That's logical in a sense, but also in the equation, if you look at it, R is in the denominator. So you want that number to be low if you want your magnetic field to be strong. Okay? Now again, if you put two wires parallel to each other, and they both have a live current, and then one of them is going to produce a magnetic field, or actually they're both going to produce magnetic field, but one of them is going to produce a magnetic field for the other, and that one is now going to be in a magnetic field, so therefore it's going to feel a force. So this is Ampere's law, and what we did just now before in the previous slide, two concepts being together. Okay? Let's do a problem. So here it says determine the force acting on the top left wire. There's one piece of information missing here, and that's the length of all of them is going to be exactly 1.0 meters. So go ahead, try and do that one. There's a lot of steps to take here, so maybe try to figure out a strategy on how to solve this problem. What's going on in that class? Everyone's just on their cell phone. Oh, it's Yael is facing the back and is on literally on the phone. Justin's leaning here talking to Danielle. Matei's laughing. You guys want to do that? I can stop. On n'a pas de cours, je vais être dans le labo si vous avez des questions, vous pouvez venir. Même chose pour mathématiques, chimie, et je pense programming too. You can go to anyone's session. You don't have to come to mine in the morning because you have class in the morning. You can come in the afternoon. Ah. All right. I want to ask you guys some questions about this problem. It says here, I want to find the force acting on this wire. That means I need to know what the magnetic field is here. Okay, so look at this one. It's a wire. It's going to produce a magnetic field, right? So if it's going into the board, there's a magnetic field going in the clockwise direction. At this point, what direction is the magnetic field? Towards the right, all right? So let me look at that. Look at that. Okay, look over there at the top. Magnetic field is pointing towards the right. That means I have a magnetic field, B. And this is B from I2. So I'm going to call this B2. There's a magnetic field being produced in that direction. And there's the same thing here. And this one is going to produce a magnetic field here. In which direction? What direction is the magnetic field at this point? Forget that there's a wire there. At this point, from this wire. So again, you go like this. So over there, in what direction is it? Up, exactly. So there's a magnetic field upwards. And I'm going to call this B3. All right. So let me ask you another question now. This thing is going to feel two different forces, right? Because it's a wire and a magnetic field. We need to use our right hand to determine which direction that force is. So I have a force coming towards you. Sorry, I have a current coming towards you. Magnetic field going there. So which direction is the force? Up. And I also have a current going there and a magnetic field going that way. Which direction is the force? Left, exactly. So I have two forces, and I have to add them up afterwards. So let's do them each individually. I'm going to do this in a different color. Let's do green, let's say. So this is going to be F2, and this is going to be F3. So my resultant force is going to be in which direction? Not 45 because they're not equal, but in somewhere between those two. All right, and that's going to be my answer, F total. Now we just have to find the magnitude of each of these and do so we're going to say F2 is going to be equal to Q. Nope, that's not the I A B. Nope, it's not I A B either. What's the formula for this? Why can't I remember? It's ILB. ILB. All right. So formulas, I can find out what the value is for each one. All lengths are 1, so that's no problem. Come on. So I have here F2 is going to be I1 times, yep. Yeah. Wrong formula. I was struggling with it. L I1 I2 over 2 pi d. You're right. And this one's going to be mu naught L times I1 times I3 over 2 pi d. once you figure out the magnitude of each force, what do you need to do? You add them, but you can't just add them 1 plus 1. Yeah, you'd have to use a Pythagoras to find out the total. So F total is going to be the square root of F2 squared plus F3 squared. And then how do you find the angle between them? Not just tan, but inverse tan of, if you want to find this angle here, it would be F2 over F3. I'm not going to ask you to plug all this in because it's just a matter of punching it into your calculator. Are there any questions on how I got this? It was a bit confusing. We're good? Okay, let's move on. We'll take a small break after this part. Okay, so solenoids are basically just a bunch of loops that are feeling a force or that are making a force, and you can figure out the direction of the magnetic field of a solenoid with the direction of the current. So if I were to draw this here the way it is, I'm going to do it in red. So I have current going up on the front side of the solenoid. So they're going up on the front side of the solenoid. The thumb is going to be pointing towards the left, and the thumb points towards the magnetic field lines, or in the case of a solenoid, where the north end of the electromagnet is. All right, so and basically the magnetic field is going towards the left. Okay. Take heed in what's in this equation and what's important. The number of loops, the length of your solenoid, and the current passing through it. So if I were to ask you to rank these in order of which they have the strongest or weakest, from going from weakest to the strongest magnetic field, how would you do it? And what I'm going to ask you guys to do, though, is not necessarily to calculate this, because that's just way too long. Try to compare these with each other. Let's say A gave us 1 unit of my magnetic field, so 1 unit equivalent of Teslas. How is B compared to A? Is it the same, the double, the half, or some other? The same, right? Because you have double the amount of loops, right, and half as much current. The radius changes though. So what's up with the radius? Let's say up there. Not important. The radius is not important. What is the radius important for? Similar to this. I'll give you a hint. It has an L in it. And I'm tricking you because the word is not with an L. Inductance. Do you guys remember inductance? No. Okay. Anyways, there's no L in inductance, it's just a symbol for it. Inductance does care about the radius. Actually, it doesn't even care about the radius, it cares about the area. Okay, moving on. So B has the same amount. So I'm going to say 1U for B as well. Okay, now how about C? It's got, and we're always comparing this back to A because that's our 1 unit reference point. It's got the same number of loops. It's twice as long and half the current, 4 times smaller. So it's going to be 0.25 units of magnetic field, right? Because remember, the longer it is, the less strong your solenoid is as a magnet. And D, compared to A, is double the length, sorry, double the loops, double the length, and 1/5 the amount of current. What would you get there? Yeah, absolutely. So 0.2, 1/5 the first one. All right, so now let's rank them in increasing order of magnetic field. It's D, then C, then A, and B. And I can put actually symbols between them. Yeah. Any questions on this? Let's take 5 minutes. Come back soon. Yeah. Flux can be two things. The magnetic field and magnetic area. One of them might be constant, the other one is going to be variable. Just on the lunch yeah. Yeah.
But like I thought about it, and then I talked to Tanya also, and she said that we concluded I might work in the sense that because the whole circuit, as I explained to you, it's supposed to like prevent an overload for the cell phone.
Right.
So like if the USB key was like overcharging, then it would have prevented it from overcharging.
Okay.
Yeah. But anyways, I talked to Tanya about it, and she agreed with me with the fact that it's possible that the circuit works because it's not destroying my phone, like the phone in a sense it's not
So
charging
okay.
because
So what
everything.
does it do then?
What that's the thing. It's like the circuit. Like as I said, I don't know. I don't know. You didn't watch my video because you didn't
No,
listen to
because
it, right? But anyways, I explained that like all the components, like all the transistors, and all that, still limits the voltage to 5.1 volts at
Okay.
1 amperage, which is like the maximum amount that a phone could take. Otherwise, it would like just die.
Okay.
So like because it shorts, well, like because I put the thing on the USB connector, the whole all the charges are going everywhere in the show like by moving my phone, like the light does come on. I don't know if
I didn't.
yeah, don't try. But you could try
But
it,
I
like,
want to get a device that I don't care about ruin, like something like
yeah. No, but I use Tiny Phone.
that. Okay.
Like I mean I could show it to you.
Like
if you want, and
she was okay with trying her phone and it worked.
it was her old, like
Okay.
it's her like daughter's phone. So, like I charge it at 1% to charge, and then I put it in. And like when you move the, you'll see in the video when I move the charger, like the light comes on.
Okay.
So like you know that there's a charge going through, and then when I leave it alone, it stops. Because like, that's when it doesn't charge anymore. It's because it's probably
Because they're overloading.
yeah, that's what we thought. Anyways,
I mean, I'll take a look at it.
yeah, sure.
If she's, I'll just ask her to come with me, and then
Yeah.
she'll tell me what you guys talked about,
Yeah,
and
because
I'll
we-
see the
I talked
video
to-
and everything.
Okay, yeah, perfect. Because I didn't explain it well. I find that like I should have. I
If
thought
I
about it
have,
after,
if I
so
have questions, I'll ask you to come in.
perfect. Thank you.
I don't know where that formula comes from. You don't need that. Just
For Giselle shows?
Yeah. Just use it the way we did it. Set up the equation, like the
You
trigonometric
have that
equation.
name.
Yeah. Okay, let's get started again. So just before we get into the hard stuff, and by hard stuff I mean induction, we did the Hall effect. And the Hall effect, if you remember, was if I were to apply a current inside a electric plate, a conductive plate, right, the current normally would just go this way. However, if there was a magnetic field, and we use all the right-hand rules and all that stuff, the magnetic field would have to be going into the plate. And what would happen is you would get a bending of the current before it crosses the plate. And that's fantastic because that bending is going to make it such that there is a voltage drop across the lateral parts of this plate, right? And so that's going to act like a source for something else. And let's say I wanted to run this into a resistor or whatever. I can make a secondary circuit coming out of my first circuit. Okay? That's quite convenient because I can start and stop this with a magnet or by providing or not providing a magnetic field in this part on that plate. The purposes of this are kind of like using magnetic card readers. That's very similar to what this is. And also hard drives, computer hard drives, use like a kind of derivative version of this, right? So they use this kind of same principle, but in a different construction. It was very theoretical, and we didn't do any calculations on this, and I plan to keep it that way. All right, so induction. And induction was the last kind of like hard chapter of the course. Then we do inductors, which was a little bit easier, but induction itself was kind of a tricky concept and relies on this concept of inertia. That inertia basically states that whatever change you have, it inertia or Mother Nature or whatever you want to call it is going to resist that change however possible. And the way that happens is, so if you increase the magnetic field inside a loop, the current will be an induced current will be made in such a way that there would be an induced magnetic field to oppose the change in the magnetic field. This relies on Faraday's law and Lenz's law. So Faraday describing the concept, and this one describing the direction. Right. So you can't have one without the other really, because they're both very important. And so of course we're going to do some example. So the first example is going to be the following. So determine the expression for change in magnetic flux with respect to the following diagram. If velocity of this object, I'm going to explain this diagram in a second. Velocity is changing. What is the current, etc. So we saw this diagram in the notes, but I just kind of changed it so that I can make a problem out of it. Imagine that this rod is all the way over here, and this rod is moving in this direction with a velocity v, and that v is described by that function. So as I'm doing this, what am I doing? Is there going to be a change in magnetic flux? Yeah, absolutely, right? The field itself doesn't change, but the area is changing. And so if the area is changing and there is magnetic field multiplied by area to give us flux, then yes, flux is also changing. So let's figure out how that's happening, right? In this case, the velocity is not constant. The velocity is changing. What's this 1.1 in front of time? It's a constant, sure. What kind of relationship is this, velocity versus time? It's linear, which means that it's the rate of change of velocity. What's the rate of change of velocity? It's the term defining the rate of change of velocity. Is what? Acceleration, exactly, right? So 1.10 is the acceleration. Do we need to know that? No, but I wanted to point that out. Okay, so there's a lot of things for us to know here. So we need to know the induced EMF. That's not even going to be the last part of the answer, because once we have the induced EMF, we have to figure out the current, or the induced current rather. So my induced EMF is always, we can always start it off by writing it this way, is the change in flux with respect to time, or the derivative of flux with respect to time. Okay? And if that were the case, then it could be the change with respect to time of b times a. And because they're perpendicular, I don't have to worry anything about direction. It's just going to be b times a. And which one of these is constant, b or a? B. Okay, so then we can write down that b with respect to the change of area with respect to time is going to give me my induced EMF. Now, how do I change? How is my magnetic field changing, or how is my area changing rather? Is it increasing or decreasing? Increasing. Well, what kind of shape do I have here? It's a rectangle. Is one side of the rectangle staying constant? Yeah, great. And that side of the rectangle is referred to as 5.0. Great. So that means I have now the E induced is going to be equal to B times the length times the change in my width, right? Because the area of a rectangle is length times width, or base times height. Do you guys prefer base times height? Let's do base times height. Base times height. And that's fantastic, because the change in the base times height is equal to velocity, right? Sorry, the change of height with respect to time is velocity. So E induced is equal to B times little b for base times velocity with respect to time. That's my expression for the induced EMF. Right? And if I want to figure out what my current is with respect to time, I can divide each one of these by resistance. So I'm going to have the induced current is equal to my magnetic field times the base of my rectangle divided by the resistance of my resistor multiplied by my velocity with respect to time. And I just need to plug in 1.22 seconds, my magnetic field, and my time, and I'll figure out what my induced current is. You're right. Anyway, yeah, no, but we did. No, we don't. I mean, the fact that we know that the definition of the change of height with respect to time is velocity. And let's say I had an expression for position with respect to time, then I'll have to find a derivative to plug it into there. Not the integral, but the derivative. Any questions? Do we need to plug in the numbers? Or are you guys okay with this? Okay? Okay, let's keep going. I have another example for you. A 5 by 5 centimeter loop with an internal resistance of 5 ohm is held stationary while the magnetic field passing through it changes with respect to time. Determine the current passing through the loop after 4.5 seconds. Okay, so again, it's going to be E induced is going to be equal to the change in flux with respect to time. This time it's not the area that's changing, the area is remaining constant, it's the magnetic field that's changing. So we can say that it's going to be area times the change in magnetic field with respect to time. So Noemi, this is going to be part of what you were just asking. What's the change of magnetic field with respect to time? Well, that's going to be the derivative of this, right? So it's going to be equal to the area multiplied by b prime of t. So we need to find what b prime is. What's the derivative of 2t? That's one of the weird ones. It's, I'll say it, it's ln of 2, or here, actually I'll write it over here if you want to take note of it. So a to the power of x, or d by dx, of a to the power of x is equal to the ln of a multiplied by a to the power of. That's the rule here. So here it's going to be ln of 2 times 2 to the power of t. Plus the derivative of t. What's the derivative of t? It's 1. 1 plus 1. Great. Now I have an expression for E induced. So E induced is going to be equal to A, which is 5 centimeters times 5 centimeters. So what is that? 0.0025 meters squared. Is that correct? Okay. And so that's my area multiplied by this function here. So ln of 2 times 2t plus 1. And in fact, here I'm asking for the current, so I have to divide both sides by r. And I have to plug in t is equal to 4.5 seconds. So I induced is going to be equal to 0.0025 meters squared divided by the resistance, which is 5 ohms, multiplied by a ln of 2 times 2 to the power of 4.5 plus 1. Did I do something wrong? Do it at 2. What? So 2 to the power of 4.5. Oh, you see, it looks, because here it looks like I wrote 2t, right? Like that. By the way, just so you know, I've also uploaded a document on Moodle for the for which derivatives, integrals, and other types of math that you're responsible for. Please take a look. In fact, I uploaded a whole bunch of stuff. Just go look at Moodle. I added a whole section for the final exam. Everything there is important. Please just read it. Any questions on this? Okay, let's move on. LR circuits. We talked about LR circuits, how it's the opposite kind of RC circuits. Slow change in current over time. There's a resist change that has to do with induction. I don't want to get too much into it. Maybe just take note that you add inductors similar to resistors. Okay, so that's something that's maybe not intuitive. So okay, here the question is: determine the expression for brightness of R3 with respect to time. So how is R3's brightness changing as time goes on? Brightness depends on which variable? Yeah. I. Okay, so that means we need to find an expression for I in order to find an expression for power, which is brightness. So let's find an expression for I here. Now, what is the current passing through this branch of the circuit? initially, how does an inductor behave? It's what? Infinite resistance, which means no current, okay? So it's got a zero current through it, and eventually that current is going to become whatever the maximum amount is. So if the current is increasing, what can you tell me about the power? Is it also increasing? Okay, so we're looking for a brightness that's going to be increasing. That's the important part. And okay, let's figure out an expression for it. First of all, we need to figure out what the the equation is, I guess. It's I with respect to time is equal to I max. And since you said it's increasing, then I know that's the 1 minus formula. So 1 minus e to the power of minus t over tau. So there's two values here that I need to learn. First of all, it's I max, what my maximum current is. And two, I need to figure out what my tau is. You said that my maximum current is going to be when my inductor is, or when the circuit just started or after a long time? Which one? After a long time, because the initial current is zero. So after a long time, an inductor behaves like a bare wire. Okay, so let's figure out what the current is through my resistance when my inductor is a bare wire. So I can ignore it. And now I have two resistors in parallel with a resistor in series. What is it? So what I'm looking for now is REQ. 141 ohms. Great. That means I have a 9-volt battery with 141 ohms in it. What's the current? Yep. Let me ask you guys a question. The current 0.06375, that's which current? The what? The current in R2, or the current leaving the battery. Is that the same current that goes into R3? No. Okay, so let's figure out which current goes into R3. So we need to figure out what the voltage drop is of R2 and then subtract that. So determine what the volt. So here we said that the current is going to be 0.06375 amps. So we can figure out the voltage of that resistor. What'd you get? 6.3, let's say 8 for simplicity's sake. And so therefore, what's the voltage drop across each of my resistors? 2.62, let's say. Volts. If that's the voltage across my two resistors, then I can find my current through that resistor, which is going to be 0.0262 amps. That is the maximum current that I'm going to get through my resistor R3. Okay, so I figured out my I max expression, 0.0262 amps. Any questions on how I got this? What's that? How did I get what? I got my voltage across R3, which we found was 2.62 volts, and then I have my resistor. So it's volts divided by resistance. I use ohms law. Next thing we need to know is what time constant we're talking about. And we have to remember the time constant is L over R. So 0.5 Henry over all the resistors that are involved. Are all the resistors involved? I think they're all involved. They're all important in some way. So that means it's going to be 100, come on, 141 ohms. Can I get a number for that? 0.00355 units. What are the units for the time constant? Seconds, exactly. Okay, great. Let's write down my expression for current. So I with respect to time is going to be equal to 0.0262 amps multiplied by 1 minus e to the power of negative t over 0.00355. That's not brightness, that's current. So I just need to square this and multiply it by r in order to find my brightness with respect to time. So I can just say now, p with respect to time is equal to I squared t multiplied by r. Right? There's some algebraic gymnastics that you have to do there if you want to do the square, because you have a subtraction there. Yep. Yes, if you find a variable expression for voltage as well, because the voltage is changing across. Right? So to me, this is more simple because you just square it. But if you were to find V, you can do it as well. We're good? All right. One more example, then we'll go into LC circuits, and that's it for today. So here it says the switch has been closed for a long time and then reopened. That means the inductor is discharging. And it says sketch the graph for the current passing through R2 with respect to time. When the switch is open, where is my current coming from? Is my voltage source involved? My battery is not involved, right? I've turned off the switch of my battery. So what's going to happen to the current, and where is the current going to come from, first of all? The inductor, because the energy is stored in the inductor, the current's going to come from the inductor, and therefore it's going to travel through which resistors? If it's coming from the inductor, is it going to go through all of them? It's not going to go through all of them because there isn't a closed circuit for all of them. So which one is not going to get a current? R2 is not getting a current. So therefore, the current in R2 with respect to time is 0. Okay, last topic. So we just need to remember a couple of things on this one. LC circuits, they bounce around energy between the inductor and the capacitor. And the fact that they're bouncing energy around means that it's an oscillating circuit, and it's going to go back and forth. And if it's lossless, this thing goes on forever. We're only going to consider lossless, so don't worry about it dying off. The frequency of the oscillations or the angular frequency, there's some expression for it. You just need to do it. So let's do the last example. All right, so I remember there being a mistake with this. Give me just 1 second. You want to create a circuit such that the alpha see it's. Oh, it says resistor here. That should not say resistor. That should say capacitor. Oh, right. And you want the angular frequency to be 500. That's what I'm saying. Frequency is how many oscillations per second, and angular frequency is how many radians per second. Great. So we have a few things to consider here. We want to know what the angular frequency, what we need to do to get an angular frequency of 500. And 500 is going to be equal to, well, we know that. I have to use one capacitor, and I have to use all three inductors. So if I have to use that capacitor, might as well go and plug in that capacitor. So it's going to be 500 going to be equal to 1 over the square root of L multiplied by C, which is not 100 ohms, but 100 farads. So let's square both sides. I'm going to get 25 or 250,000 is equal to 1 over L times 100. Is that right? 500 squared is 250,000 or 25,000? It's okay? And so therefore L is going to be equal to a really small number, 1 over 2.5 million. Is that right? No, eh? It's not 2.5 million, is it 8? Yeah, like that. Yeah. Someone get a number? What? À la moins 4? Je pense qu'il y a une erreur avec l'exposant. C'est 2.5 fois 10 à la moins 8. Vas-y, petit gars. Yeah, that's correct. And that is the same as saying 40 nanohenry. So how do we arrange 3 inductors so that we get 40 nanohenry? So now we just need to, there's three, and I can only use each one once. How can I arrange them so that my total equivalent inductance is 40 nanohenry? Yeah? Oh, minus 9? I agree with the minus 8. It could be 40 to the power of minus 9, or 4 times 10 to the minus 8. Unless I made a mistake somewhere else before, I expected the answer to be 40. And correct for that. So you were right the first time? Okay. Does that mean Zach was wrong for the first time? Can I add them all in series? No, definitely not in series, because if I add them up, it's 25 plus 20 plus 60, that's 105. That's not what I want. I want something that's smaller than 60. So 60 definitely needs to be in parallel with something else. Yeah. Exactly, yeah. So here's my 100 farad capacitor, my inductor at 25 and then another inductor here, and another inductor here. This one's going to be 20, and this one's going to be 60. Nanohenry. Nanohenry. Does that make sense? All right. So that's the last word. I want to wish you guys good luck on your exam. If I don't see you, it's been a pleasure. Right? I hope I see you guys again next semester. Like it's always funny. We get our reviews, and there's always like two students who are like, "Worst human being ever. Should kill himself." So if you're those two students, don't take my class. And otherwise, please take my class. Yeah.